Washington State University. Go Cougs!
Hello everyone. In this video, we're going to cover Lesson 7, the last lesson of the Activity Change Detection module. In the previous lesson, we began our discussion of the virtual classifier as our change score function f as part of our PACD framework. We began implementing the virtual classifier algorithm, and in this video, we're going to finish that implementation. So let's pick up where we left off by reading in our Fitbit example data features df CSV file that we wrote out in our previous lesson. I have code here that's going to read it in. And just to review the format of this data frame, let's print it out. So this is the data frame we wrote out in our previous lesson, where our index included our 21 days and our columns were features for each day. So this is our Fitbit example data features DF that we wrote out in our last lesson. So now we're going to implement the next step of the virtual classifier algorithm, which is to label our windows as either a positive or a negative class. So our first window will be W sub 1 starting at the first day, and it will contain 7 days worth of data for the first 7 days or the first week of our data frame. And then this will be a positive class, and our negative class will be the next week, which will be the next 7 days. So let's write a function to do this. Let's call it label windows, and it will accept features data frame. I'm going to make a note here saying this function is going to be hard-coded for W1 and W8, which will be the first and the second week of the data in features DF. If we wanted to make this code extensible, we should pass in an argument specifying the size of the window and use that for our slices. But for now, in the sake of time, we'll just go ahead and hard code it for 7 days for week 1 and week 2, W sub 1 and W sub 8 for our windows. So first thing, let's go ahead and add another column called class to our data frame. And we'll initialize this to missing values, NaNs, and then we will immediately set the first 7 days class label to be 1, and we'll do the same thing for the next 7 days, which is our second window. We'll set that class label to be -1. Then we'll go ahead and extract the feature set for window 1 called F1, and again the feature set for window sub 8, our second window, called F8. And these two data frames representing our sets of features in our positive and our negative class will be the return values from these functions. Next, we call label windows, passing in our features data frame, and let's just confirm that the length of F1 is the same as the length of F8, just to ensure that these are equal size windows, and we get true. So this looks good. Now the next step is to train our binary classifier to discriminate between our feature vectors in F1 and our feature vectors in F8. To do this, we're going to use the Python machine learning library scikit-learn. Scikit-learn has a decision tree classifier that we can use to construct a model to discriminate between F1 and F8. Let's write a function to do this. We'll call this function compute VC change score. And it will accept 2 windows, which I'm going to write more generally as F sub I and F sub j, corresponding to windows W sub I and W sub j. So first thing, we're going to concatenate these 2 feature vector sets into one. So we're going to mix our classes up. To do this, we'll use the concatenate function from pandas and concatenate fi and fj, and these have the same columns. Then we're going to go ahead and grab all of our features that will be used for training. We can do that by indexing. We can do that by dropping the class column from our FAll data frame. And then we'll grab our ground truth labels. These are going to be our class labels. I'll call this FAll Y. And that will simply be the class column. Now we're ready to construct our decision tree classifier. Set the random state to be 0. We're going to call the cross-val score function from scikit-learn that has a few arguments. The first one is going to be the classifier to use in k-fold cross-validation, which is CLF. The next one is going to be our training examples, or all of our examples that do not have their ground truth labels associated with them. So that would be FAll X, and then the ground truth labels for our FAll X, which is FAll Y, and then CV is a keyword argument to set the number of stratified k-fold in cross-validation. So I'm going to set this to just be 7, which is the size of our data set divided by 2. Let's take a look at cross-val score. So we can see how these arguments I'm passing in are going to line up with our model. So the first argument is our estimator. So that is CLF. That is our decision tree classifier. Then there's X, which is the data to fit. Can be a list or an array at least 2D. And then Y is our target variable. So this is our class label. So you can think of X as our entire data set for our first window and our second window without the class label. And you can think about Y as being our class label for all of our instances in X. And then here is CV. This is the cross-validation generator, or an iterable or an integer. We're passing in an integer, which is going to specify the number of folds in a stratified k-fold cross-validation. And one last thing to show you is what this function returns: an array of scores of the estimator for each run of cross-validation. So this is going to return a list of 7 items, where each item is going to be the prediction accuracy for a run of stratified k-fold cross-validation. So we're not interested in each fold score necessarily, but the average of all of the scores. And we can get that by using NumPy. And that will be our return value. Now I'm going to call compute BC change score, passing in F1 and F8, and I'm going to save the return value in a variable called PVC. This is the prediction accuracy for our virtual classifier, just to be consistent with our notation that we've been using so far. For example, PVC listed here. Now I run this, and the prediction accuracy for our first week and our second week of our example Fitbit data is 0.43, which is quite low. In fact, we don't even need to do a significance test to know this isn't a significant change, because for 2 equal size windows of random data, we would expect accuracy of about 0.5 due to a binomial distribution. So we know this is not significant, but we're going to look at a few examples here shortly where we do have significant changes. Now that we've computed PVC, the next step is to define our significance test to determine if PVC is significantly large to denote a significant change between our two windows, W sub I and W sub j. So to do this, we're going to make use of a function called compute binomial critical probability that accepts three parameters, alpha significance level, an n number of trials, and prand, the probability expected from random data. Now, this function is going to make use of a SciPy stats function from the binomial distribution called ISF, short for inverse survival function. So what this function is going to determine is, after n trials, what is the value that is greater than our random probability with significance level alpha. So here are our parameters. Alpha is 0.05, common significance level. N is going to be 14, which is going to be the number of features vectors. So length of F1 plus length of F8. Prand is going to be set to 0.5 because our two windows, our positive and our negative examples, are of equal length. And pcritical will be the return value from a call to this function here. Now, we can set a flag called isSig, short for isSignificant, to 1 if PBC is greater than or equal to precritical. That's the implementation of this line here. Otherwise, we'll set it to 0. So if isSig is 1, then it's significant. If it's 0, then it is not. And we run this code. We see that our p-critical value is 0.71. 0.43 is not greater than or equal to 0.71, so this is not a significant result. I've included some other examples here so you can see what values of PBC are going to be significant. So here, I have included 4 examples called HS1 through 4 that represent hybrid synthetic data. What I've done is taken real Fitbit data from a volunteer and forced some changes to occur in the data between two windows of 7 days each. That way we can see what are the change scores related to some of these forced changes. Without going into too much detail about how the data was sampled, if you're interested, you can read more in our paper. I've included ADMs so you can see what the changes look like. So, for example, hybrid synthetic profile number 1, you can see that there is an increase in intensity from the beginning of the 2-week span to the end of the 2-week span. So I've included our code to compute the features for this data and run the virtual classifier. So let's run it for our hybrid synthetic data set profile number 1 and see what the change score is. So the change score here, PBC, is 0.93, which is above 0.71, so this is a significant change. So between our first 7 days and our second 7 days, with intensity increase, there is a significant change here. Another example is hybrid synthetic profile 2, which has several changes, as you can see, between our first week and our second week. Our first week is fairly similar from day to day, and our second week is quite different from day to day, with some increased number of bouts and intensity. So let's run this. Here, PBC is 1, which is definitely significant, so the virtual classifier can easily detect this type of change. Here's another example where we have very similar day-to-day change gradually increasing as we move towards the end of the 2 weeks. And we can see at the end of the 2 weeks, we definitely have quite a bit of change between the days. So this probability for PBC is 0.93, which is significant. And the last example here is very similar day-to-day change in the first week, and then very, very, very different day-to-day change in the second week. And we'll see that this has a probability for PBC of 1. So this is definitely significant. So this is just supposed to give you an example of some of the changes that can be picked up quite easily with the virtual classifier. For our real example, we did not see a significant change in this data set. But if you're interested in seeing some other real-world data sets that do have significant change, I recommend you check out our paper that a link is included here.